Alright, welcome to Newton's second law. Newton's second law basically says the acceleration an object experiences is equal to the force applied to the object divided by the mass of the object. So acceleration goes up with force and down with mass. So we often write it this way, A equals F over M, or sometimes, and more frequently actually, we write it as F equals MA. So let's get started. The box is being pulled to the right across a frictionless surface, and our tension is 170 newtons of force. Remember, force is measured in newtons. As a result, it is accelerating at this fast, so I want to find the mass. So I'm going to use the equation, this equation right here, F equals ma, and I'm going to substitute in. So for force, I'm going to put 170 newtons equals the mass, which is what I'm looking for, times the acceleration. Now in this case, it is accelerating in a positive direction, so I'll say 3.2 meters per second squared. And when I solve that for m, I'll find the mass of the box is about 53 kilograms. Now the next one, I have a box is sliding to the right at 22 meters per second, but it is encountering 180 newtons of friction, and friction is always in the opposite direction of motion. So that's 180 newtons in the negative direction. What is the acceleration of the box? So I'm going to use this version of the equation here. Since I'm solving for acceleration, I'll say A equals F over m. So the acceleration is going to be equal to the force, which is negative 180 newtons because it is oriented in the negative direction, divided by the mass of the box, which is 45 kilograms. And it may not be immediately evident that when you divide newtons by kilograms you get meters per second squared, but you do. So when I divide those, what I'll get is negative 4 meters per second squared. Now, how far away will it be? I'm looking for distance. So we have to be able to combine the Newton's second law with kinematics. That's huge in AP Physics. You often will have a problem where you have to combine these two. So let's just see what equation would I have to use. Well, if I look, I know that I have a uniform acceleration. I know that I have an initial velocity. I know that I have time, and I'm looking for distance. So the kinematics equation that's going to work in this case is x equals x naught plus v naught t plus 1/2 at squared. That's the kinematics equation that's going to work. I'm going to substitute into that. So I'm looking for the distance. I don't know what that is, so x is going to equal the original position, which we'll call 0, plus the original velocity, which is positive 22 meters per second, times 3 seconds, plus the acceleration, which 1/2 the acceleration, so plus 1/2 the acceleration, which is negative 4, times the time squared. And when I solve for that, what I'll find is the amount of displacement will be a positive displacement, and it will be 48 meters. Keeping going, number 3, I have a rocket traveling through space in the positive direction, and the force acting on it is in the negative direction. So it's a lot like what we saw up above. So I've got a rocket that is moving in the positive direction. So let me just draw a rocket. I have a rocket moving in the positive direction. So that's its velocity, but the force is acting in the negative direction, which means it's got a negative acceleration. So what is the rocket's acceleration? I'm going to use A equals F over m. A equals, in this case, it's negative 18,000 newtons divided by the mass of the rocket, which is 4,000 kilograms. And by the way, it is really important to learn your units. If you don't learn your units, these equations do you basically no good. And what I find then is the acceleration of the rocket is negative 4.5 meters per second squared. So every second it's going to slow down. well, it's going to be accelerated 4.5 meters per second in the negative direction. How fast and which way does the rocket end up going in 55 seconds? Well, if I'm going to solve that, I need to use this kinematics equation. Let's see what I know. I have a time, I have an acceleration, I have an initial velocity, and I'm looking for a final velocity. So that sounds to me like I should be using v equals v naught, that's a naught, plus at. So my final velocity I'm looking for, my initial velocity was positive 220 plus negative 4.5 meters per second squared times a time of 55. And that's going to give me the final velocity. And when I solve for that final velocity, what I'm going to find is my final velocity, in this case, is going to be negative 27.5 meters per second. In other words, this rocket is going to slow down, since it's moving this way and the force is this way, it's going to have a negative acceleration, so it's going to slow down. Remember, a negative acceleration means to slow down in the positive direction and then speed up in the negative direction. Well, how fast would the rocket end up going if the engines produced twice as much force? So if I double the force, I'm going to double the acceleration. So instead of negative 4.5, the acceleration is going to be negative 9 meters per second squared. So I'm going to use my kinematics equation again, but this time using negative 9 instead of negative 4, because double the force, you double the acceleration. So in this case, what I would have is the v equals 220 plus negative 9 times 55. And when I solve for that, what I'll find is v, in this case, will equal negative 275. Let's try our next one. The diagram above shows two boxes. Now, with the trick to these types of pulled box problems, which are very commonly asked on AP tests, is that the total mass of the system is accelerating this way at 6 meters per second squared. Now, so this string is pulling the whole system, so I had to consider the whole mass and this acceleration, but this box here is being pulled by this string here, and I only have this mass that's accelerating. So let's try it. What is the magnitude of T1? T1 is pulling the whole system, so I have to add up all the force here. So I'm going to say the tension force equals MA, so force equals MA, let's substitute in, force equals, the mass is going to be 8 kilograms plus 14 kilograms, and that's going to be times the acceleration, which is times 6 meters per second squared. And therefore the tension is going to be 132 newtons. So this tension is 132 newtons. What is the magnitude of tension T2? Well, in this case, this string here is only pulling this box. Now it's making it accelerate at the same speed because the whole system is accelerating this fast. So I keep the same acceleration, but in this case I say, well, the force T2 is going to equal the mass of just that second box, this one right here. So it's the mass of the second box, 8 kilograms, times the acceleration of the system, which is 6 meters per second squared. And unless I'm wrong, 8 times 6 is 48 newtons. So this one is 48 newtons. Alright, on number 5, I have two boxes. Box 1 is experiencing T2. The whole system is experiencing T1, which is 165. So let's see what we've got to find out here. What is the magnitude of T2? So I'm wondering the magnitude of this force is acting on this mass, causing it to accelerate this fast. So I'll say the force T2 is equal to the mass of 11 kilograms times the acceleration, which is right here, 3 meters per second squared. And that's going to give me a force of 33 newtons. I'll just write that here, 33 newtons. Now the next one is, what is the mass of box A? So I want to know what the mass of this is. That means, well, so here's what I know, that the whole system here is subject to this force, so this tension here is acting on the whole system. So I'm going to take this tension here and use that as the force in F equals ma. So I'm going to say 165 newtons equals, for the mass, I have to say 11 kilograms plus, I'll just say m sub a, so the mass of A, and that's all times the acceleration, which is 3 meters per second squared. And what I want to find is ma. So what I'm going to do is I'm going to multiply through, I'm going to distribute this around, so this is going to be 33 plus 3 ma. So 165 equals 33 plus 3 ma. So I'm going to subtract 33 from both sides, and when I do that I get I get 132 equals 3 ma. And now when I divide both sides by 3, what I find is the mass of A equals, what's it equal? It equals 44 kilograms. So I'll put it here. Isn't this empowering? Okay, well let's try the next one. I love these double box problems. Alright, so here we go. I had two boxes connected by ropes accelerating across the frictionless surface. This time I don't know how fast it's accelerating, and that's what I'm supposed to find out. How fast is it accelerating? So I'm going to say A equals F over M. But the catch here is I can't really answer the question for the whole system because I don't know what the force on the whole system is. But I do know this. If you pull on this one here, the whole system has to accelerate uniformly. You can't have this box accelerating any faster or slower than this one, and vice versa. So therefore, if I find the acceleration of this part of the system, then I have found the acceleration for the whole system. So I'm just going to focus on this part here. So I'm going to say, well, the force acting on that part, the tension force acting there is 165 newtons, and that's acting on 88 kilograms. And 165 divided by 88 is 1.875 meters per second squared. And now the deal is, if this part is accelerating at 1.875 meters per second squared, so is the whole kit and caboodle. So that's how I'm going to solve for this one here. What's at tension T1? So I'm looking for an F. I'm going to say F T1 equals the mass of the system, which is 44 plus 88. So all I did is I just took the total mass of the system, and I'm going to multiply it by the acceleration of the system, which I found. So times 1.875, and you know what? The tension force on T1 therefore equals 247.5 newtons. 247.5 newtons. A student attaches a spring scale to a 1.5 kilogram book and measures the force between the book and the tail to be 2. Now remember, friction always acts opposite the motion. She then gives the book and sets it in motion. The book is traveling at 4 when it leaves her hand. You know, I'm just going to draw myself a diagram. Here's the table. Here's the book. The book is traveling, the velocity is this way, and the velocity is 4 meters per second. The friction is this way. It's always against motion, and it's 2 newtons. And what I want to know is how fast will the book be going when it's 2.5 meters away. So I'm looking for a velocity when I have a given distance. And when you're asked basically what amounts to a kinematics problem, how fast, how far, you need to figure the acceleration. Because with kinematics equations, there's always a uniform acceleration, and that's where this information is going to come in. I'm going to use F equals ma to figure out what the acceleration is. So my book is 1.5 kilograms. So the first thing I'm going to do is I'm going to say acceleration equals force over mass. In this case, the force is negative 2 newtons, and the mass is 1.5 kilograms. So therefore the acceleration on the system is negative 1.3 meters per second squared. Now that I know the acceleration, I have one velocity, which is here, and I want to know the ending velocity, and I know the acceleration and the distance, but I don't know the time. I know which kinematics equation that's going to be. I'm going to use this one here. I'm going to say v squared equals v naught squared plus 2a delta x. Now I'm going to substitute, but I'm going to move myself over a little bit here. So what I'm looking for is v2. I'm looking for v. So I have v squared equals v naught is 4 meters per second. That's how fast it was going initially. So I'm going to say 4 meters per second squared plus 2 times the acceleration, and the acceleration I found to be negative 1.3 meters per second squared times the change in position. The change in position is 2.5 meters. And I'm solving that. So what I'm going to get is this: v squared equals 9.3. So then what I'm going to do is I'm going to take the square root. I'm going to take the square root of both sides. And what I find is the velocity that it ends up with, which has to be less than 4, ends up being 3 meters per second. It's actually 3.0 something. Okay, well, we're going to one significant figure, or even to two significant figures, it's 3. Okay. Last one. A car is towed by a rope. Now let's see, and the car is going, both cars, the light turns green, the car's beginning to accelerate. You know, darn it, I guess it would have helped if we saw which way. I thought you could tell by looking at the cars that the cars are accelerating this way, which is what my intention was. I guess I should have drawn that. Okay, but here we go. What is the force produced by the engine? Well, let's see. I'm looking for the force. To know the force, I have to know the mass. I got the mass. I need to know the acceleration. You know what? I wasn't told how fast they're accelerating, so I'm going to have to figure it out. Now, what do I know? I know a distance, I know a time, and I'm asked to find an acceleration. I think I'm going to say, since they're starting at rest, both cars are initially at rest, I'm going to use this equation here. D equals 1/2 AT squared. For distance, I'm going to put in 72 equals 1/2 A times 6 squared. And when I solve that for A, what I'm going to find is the acceleration in this case is 4 meters per second squared. I seem to like that number, don't I? But the question is, what is the force? So the force produced by this car is accelerating the whole system. So I'm going to say that the force equals MA. The M is going to be 600 kilograms plus 800 kilograms. And the acceleration is 4. And when I solve that, 600 plus 800 times 4, I'll get 5,600 newtons, which I'll then put here. 5,600 newtons is acting on this system. Well, that's the case. What is the tension on this rope right here? So now I just have to concern myself with this part of the system. So I know how fast it was. So basically, if I want to find the tension, that's a force. I'll say force equals mass times acceleration. In this case, the mass I'm concerned with is the mass of this car, because that's the one that's being accelerated by this force. This force does not accelerate that mass, it only accelerates this mass. So the mass in question is going to be 600. That's not a very good 6. And the acceleration is 4 meters per second squared. 600 times 4, 2,400 newtons. So this is 2,400 newtons. If the rope connecting the cars breaks when the tension force exceeds 3,000 newtons, what is the fastest that car A can accelerate without detaching by breaking this rope? So the way I'm going to solve this is I'm going to take the maximum force and I'm going to use that in Newton's second law. So force equals MA, and I want to solve that for A. So the maximum force I could have is 3,000 newtons. Anything beyond that, it breaks. The mass of the car I'm accelerating is 600 kilograms, so I put 600 here times A. So I simply have to divide both sides by 600. And when I do that, I'll find that A equals 5 meters per second squared. That's Newton's second law. If you've got this down, you are in great shape. This is really a huge amount of what physics comes down to, is the connection or interconnectedness between kinematics and the ability to calculate acceleration based on force and mass. So if you've got this down, good on you. If not, talk to me. We've got to get you caught up on it because this is a really, really important concept in physics. This is Eric Sampson signing off.